Greetings to anybody who's watching this video right now. This is group 706 under the guidance of Dr. Shilpa Chaudhary. My name is Daanish Khan and I am going to present our project which we have developed called Fragment 3D based on the existing project Part Packer. Our goal was to move beyond standard 3D generation and tackle the problem of structural understanding in neural networks. Now let us first look at the problem, which is how current models are very excellent at generating visual forms, but they typically output a single fused mesh, and this lacks utility because you cannot edit individual parts like a separate part of a body, be it a hand or a tire of a car. And this is how our framework introduces the solution, which is a dual volume packing strategy. We process the geometry not as a single solid but as distinct volumes that can be separated. This allows us to generate 3D objects with editable, semantically meaningful parts in approximately 30 seconds, more or less. Now here's the architecture diagram. We have made some changes if you have seen the previous milestone video. Now let's look at it. Now, firstly, the front end, we use this is like client side application. We built this using React because it is rapid, responsive, a single page application. Now here the user uploads a single 2D image, which means a raw 2D image having only 2 dimensions. Now we handle immediate validation here before sending anything to the server. Now coming to the middleware, here is how the orchestration and security happens. This is built on Node.js and Express.js. Now we manage our authentication securely using the post or register and post or login endpoints, and then asset management using post or upload image endpoint. This is when the user uploads an image, and then MongoDB to store user profiles and assess the data. We chose NoSQL because the data for 3D assets varies and it requires a flexible schema. And the Grad.io API, which is the inference engine, it allows us to decouple the heavy GPU it allows us to decouple the heavy GPU compute from our lightweight web server. You can see how this takes place step by step, from the Dyno V2 encoder to the generative process, and the dual volume packing strategy, and finally the triplanar extraction. Now once the 3D mesh is generated, the Grad.io API sends the file back to the middleware via the the GLB checkpoint, GLB endpoint, which saves the link in MongoDB and serves it back to the React front end for the user to wave it and use it for whatever purpose they have. The tech stack, you can see what the tech stack we have used, which is firstly the language Python and the framework PyTorch. Now what's crucial for 3D representations is the NVIDIA Tiny CUDA NN library. It allows us to use fast hash grid representations, which is how we accelerate this process compared to standard voxel grids. Let us move on to the maths section of the video. Now firstly, what happens is the latent decoding. Now what we give to our system, the input to our system would be a compressed latent representation, which is denoted by Z, and then we pass this through a transformer decoder which maps this Z into a global hidden states H. Now the main important thing here is the section 2.1, which is a global feature projection. Firstly, we compute a global descriptor H global. Now by averaging these transformer outputs, then instead of expanding this into a 3D volume, we linearly project this into a single vector into 3 orthogonal features. And then the section 2.0, bilinear sampling from triplanar features. This is for the sampling and aggregation. We define query points P in the coordinates in the 3D space, and then we perform bilinear sampling using bilinear interpolation. And then finally section 2.3, triplanar feature aggregation. The feature is obtained by averaging contributions from all 3 planes. Now that we have seen what the architecture is and what the math behind it is, here's the live implementation of our project. So here's a live demo of our project. We are not doing it actually live right now, because this is very computationally heavy, so we just had someone do it once, and our entire team has used it. And as you can see, our single web page application with sign in and registering option. These are the objects which we have already created. Now we're going to do it with a new image. We also have a delete option. We also have a random seed option. You can also custom choose it. Firstly, we have chosen a chair as an object, and then the API calling takes place, and then a 3D model is formed. I'm just going to fast forward it because It takes a bit of a time. You can see. Yeah. So we have two different colors for two different parts, and you can scroll it and view different parts being separated in live, and then a different object similarly. Your generated objects will be stored in your my objects section. And here's another example, a part separable mesh. And this is the other one. This is the third one with another example, part separable mesh. Thank you. Let's move on with our presentation. Now, here are the real world applications. This is how a project plays a crucial role in overcoming these problems in game development and simulation and content creation, uh, which is related to 3. Now, the primary challenge we faced was the computational cost. The 3D generation is inherently very memory intensive, so we overcame this by implementing a triplanar feature projection, which we just discussed, and by compressing 3D space into orthogonal 2D planes, we reduced the memory overhead by approximately 60%, while also maintaining distinct part separability. Now, to conclude, Fragment 3D contributes the vision of human-centered 3D creativity. We are enabling neural networks to go beyond replicating visual forms. We are teaching them how to understand and generate structural logic behind them. Thank you.